Okay, so today I'm gonna continue about likelihood-based estimation of DSGE models and what Dinair can do. So Dinair, we've seen that Dinair has an estimation command, and we've already discussed how to do maximum likelihood estimation with this estimation command, and we even replicated this result by ourselves. However, this command can also do so-called Bayesian MCMC methods, and then you can do all sorts of analysis. Now, let me quickly recap what we've seen when we talked about Bayesian estimation of VAR models. So the idea was that we wanted to use data to learn about something unknown, which will be our model parameters, shock parameters, given something known, the data. Now, the maximum likelihood approach or the frequentist approach is to think about there is one true value of parameters. And then we come up with an estimating function, say the mean or so, and that is a random variable. The law of large number tells me that it converges to the true value, and a central limit theorem most of the times provides me with uncertainty of this estimating function. Now, the estimator is best in the sense of having the highest probability of being close to the true parameter. The Bayesian approach is, philosophically speaking, different. Okay, so there is not one true parameter vector, but parameters are random variables characterized by a probability distribution. And we call this probability distribution the posterior distribution. It combines two things: the priors, that is information that I have before seeing the data, times the likelihood, that is the information stemming from the data. And prior information is our subjective beliefs about how we think that parameters, how likely they are before we see the data. That's important. And then we update this prior information after seeing the data via the likelihood, via the sample information. Now, Bayesian simulation methods or sampling methods, they provide a very easy way and very straightforward way to characterize estimation uncertainty, because we are looking at posterior distributions, and we want to describe distribution by statistics, say the mode, the mean, variance, quantiles, areas with a high posterior density, etc. Now, because we include additional information, this typically adds to the precision of our estimates and makes them also often more feasible in economic terms. So we do not run into situations where an optimization algorithm tries out certain parameter values that we would consider economically wrong, say like a discount factor being larger than 1. Now, what are the ingredients? The ingredients are the prior and the likelihood, and we combine that by Bayes' rule. Okay, so remember the formulas from undergraduate statistics for the joint probability of two events A and B. The probability of them happening jointly is equal to the conditional probability of A, given that B happened, times the probability that B happened. And we can turn this around and combine the formula, and then we get Bayes' rule. And Bayes' rule also works for continuous distribution. So we have the posterior distribution right here, we have the likelihood right here, and the prior right there. And in the denominator, we have the marginal data density, which is not a function of the parameter. So in terms of estimation, I don't really care about this, but I want to look at this posterior distribution. So this is the proportional to sign. How do we compute the likelihood of a DSGE model? Well, we did this in the last lecture. When we discussed first order perturbation solution is given by these transition equation. And if we combine this transition equation with a measurement equation, which basically selects the variables that are observable, I have a so-called linear Gaussian state space system. And we've seen how this works. The transition equation is, in the statistical literature, this will be called the equation for my states. Y, in our case, we call those model variables. And then our measurement equation would be the equation for control variables. For us, this is the subset of model variables that are observable. And everything is linear, and there are two innovations to both equations. One, in the transition equation, we add the shocks, u, they are Gaussian with some covariance matrix, sigma u, and the measurement equation possibly also has measurement errors or noise. Now, because we do not observe all the model variables and we can only base our estimation on a subsample of variables, we need a tool to evaluate the likelihood for any parameter. And the tool that is most capable to do this is the so-called Kalman filter, and this makes use of the assumptions of a linear system with everything being normally distributed. The problem that the Kalman filter solves is that when we want to compute the likelihood of our data, the mean and the covariance depend on unobserved state variables yt minus 1. So we cannot really construct the Gaussian likelihood directly, but the filter enables us to compute recursive best estimates for this mean and this covariance matrix of the unobserved yt by backing these out from real data and our predictions that we make given a certain information set. This works for first-order perturbation approximation, and we've seen that in the last lecture. Different solution algorithms require you to use different filtering techniques, but this becomes much more complicated and less feasible and computationally much more expensive. So, we know how to compute the likelihood. We've done this in the last lecture. We even maximized the likelihood. Now, how can we combine this with priors? We just multiply that, or take the log and then we add the log prior plus the log likelihood to get the log posterior. But what priors should we choose? Now, ideally, you can really formulate mathematically your prior belief on the parameter before seeing the data. Now, realistically speaking, you do have additional information from similar studies. Say you have a paper on US data and you want to do a similar analysis for Italian data, then of course this will guide your prior beliefs. What we need here is actually a multivariate prior. So for each of the parameters, for the discount factor, for the depreciation rate, for all the autoregressive coefficients, for steady state parameters, etc., we need prior distributions. Very importantly, this is different to the multivariate vector autoregressive model, where we needed to put priors on the A matrix, or the A1, the A2, so the lag matrices, and we did this, for instance, with a Minnesota prior. This is very different to what we are doing here now. We have priors for the underlying structural model parameters, and they, by the perturbation solution, provide me with a gx and a gu, so the reduced form that looks similar to a vector autoregressive model of order 1. But very importantly, let me be very clear on this, my prior is on the underlying model parameters, not on gx, gu. These are just functions of my parameters theta. Now, and we need a multivariate prior. So in principle, we could say that there is dependence, some dependence structure. Okay, so if a parameter is very high, another parameter, I think that must be very low. So that is totally fine. You can come up with this. In most studies, however, you will find that we usually specify independent priors for each parameter individually. Now, whether this is a good choice or not, that's up to you to decide. So what are typical choices? Well, typical choices that are easily accessible also in the estimated params block of Dinair are, for instance, the normal distribution. This is a distribution with an unbounded support. It is symmetric. And this is typically used for feedback parameters or when you do not know the sign of a parameter. Then there is the uniform distribution, where you need to specify, say, a lower and upper bound, and all the points in between these bounds are equally likely. That's a so-called flat prior, very often used for parameters that are distributed between, say, 0 and 1. Another important prior that provides you a bounded support between 2 points, mostly say between 0 and 1, is the beta prior. And this is very often used for autoregressive parameters because it puts, you can put mass rather towards 1 or rather towards 0 or have even a symmetric shape. Then the beta distribution is a very good choice. So you will find this is a typical choice for autoregressive parameters of shock transition equations, for discount factors, or probabilities like the Calvo probability of price rigidities. Then there are two also very important distributions, the gamma and the inverse gamma distributions. Those are very often used to put priors on variances or standard errors that you want to estimate, or parameters that are positive, because both distributions have a support on positive numbers. The gamma also includes the 0, the inverse gamma does not. So very often used for, say, feedback parameters or large variances. When you have that or suspect that, then the gamma distribution is used. If you have rather small variances or standard error parameters, then the inverse gamma is a typical choice. Okay, so now we have discussed how to set up your priors. The Kalman filter enables us to compute the likelihood, but how do we actually get the posterior distribution? So the problem that we're faced with is that the posterior is typically not analytical. So there is like no closed form like a normal distribution or a gamma distribution where we can easily plot it or draw from it or compute statistics on that. But let's put the problem differently. So I am not really interested in the exact shape of this distribution, but I am typically interested in statistics on this distribution. So I'm interested in the mean, in the variance, or some other function, some interval that has a certain amount of density under the curve. Those are the statistics that we're typically interested in. And the key point is the law of large numbers that we can make use of. So all these statistics are integrals. And if we somehow can get identically independent distributed draws from the posterior, so IID draws, then we can replace integrals by sums. We need a large amount of draws, but then whenever we're faced with an integral, we can just use the average on this statistic. So if you're interested in the mean, you just try to get 1,000,000 in IID draws and then you just take the average. If you're interested in a variance, you take this 1,000,000 of IID draws and compute the variance on that, or the skewness coefficient or the kurtosis. And the law of large number tells you that if you have IID draws, you can replace your integral with the sum. And this is called Monte Carlo integration. Okay, so of course this is just an estimate. How good is this estimate? Well, the law of large number tells you that it will converge to the true value there, and the central limit theorem gives your asymptotic normality if you have IID draws. But you need to get those draws first. Okay, so how do we get those theta S, theta 1, theta 2, theta 3, those 1,000,000 draws? And there are different so-called sampling algorithms. But I'm gonna only talk about the Metropolis Hastings algorithm here, because this is what Dinaire uses by default when you do Bayesian estimation at first order. Now, what is the key idea of this algorithm? Again, the problem is we cannot get random draws from the posterior directly, but what we can do is we can evaluate the prior and the likelihood, so we can actually compute the posterior for any parameter that there is. Remember when we did maximum likelihood, an optimizer tried out in a sophisticated way, tried to find the parameter vector that maximized the likelihood. So we were able to compute the likelihood for any parameter draw that is within a feasible domain. Okay. Now, the key idea of the Metropolis Hastings algorithm is if we can do this, we need to add randomness and importance of those draws, those vectors of parameters. And the idea is, all right, let's use a stand-in distribution or some other easy to draw from distribution, a so-called proposal distribution, get random draws from that one, and then evaluate both your proposal and your target posterior, your target density, and then have a formula, make a decision, how much weight does this draw get in the distribution. So you're comparing densities. And the intuition of the Metropolis Hastings algorithm is wherever you start, if the posterior is higher for a new draw than where you're currently at, you will always jump uphill. Okay, so you will always try to get to the mode of your distribution. So always jump uphill, and this jump will get a high weight. However, you also, every once in a while, want to go down again. So you do want to jump downhill, not always, but sometimes. And we're going to use a random probability to decide whenever we want to go down or not. And the idea here is we want to visit the whole domain of the posterior. So let me sketch the algorithm in generic terms. So you start somewhere. Let's say you want to estimate the autoregressive coefficient of a TFP process. So you start at 0.5. And then you want to get 1 million draws from the posterior. You need to decide on a proposal. Let's call this proposal Q. And you see that Q is defined as I get a new draw, a new theta, given my old draw, j minus 1, because the previous value impacts your next value. Now, what are typical choices for the proposal? Let's take this default assumption of a normal distribution, where we recenter it at theta 0 in the very first step, and then at the next accepted draw, theta j minus 1 to get theta j. So it's a normal, it always has the same covariance matrix sigma. There is no j-index there. So it has a certain width, this normal distribution, and it gets recentered. It jumps around, left, right, and then we draw from this normal distribution. So we get a candidate draw, let's call this theta tilde. And then we're going to compute the so-called acceptance probability. So we are going to evaluate the posterior at my new draw, that's right here, in the numerator, and compare this to the posterior where I'm currently at my old draw. Remember, the idea is always jump uphill and sometimes jump downhill. So if this probability, this alpha, is 1 or higher, so if my value of the posterior density function is larger than my old value, I accept the jump. I have a draw, okay? So I accept the jump from theta j minus 1 to theta tilde, and I call this theta tilde then theta j. And I'll increase my j and go to 2. Now, I don't accept the jump with the complementary probability. So if this alpha is less than 1, then I'm not gonna reject this immediately, but I'm gonna flip a coin, more or less. Okay, so say your alpha is 0.5. Then I'm gonna draw another random variable, let's call this r, which is between 0 and 1, so which is like a probability. And if this random variable is less or equal to alpha, then I'm going to accept. If not, I'm going to discard. And in this way, I always go uphill, but sometimes I do go downhill and accept the draw and try to visit the whole domain of the posterior. Now, this sounds very complicated, but this is actually really easy. Let me demonstrate this. Assume that this black line is the posterior, the true posterior distribution, and I don't know this distribution. So the first step is we have to find a proposal distribution, and we're going to use a normal distribution for this. The green curve is the proposal distribution, the normal distribution. It is centered at this value right here. Now the black line, the black vertical line right here, is a new draw from this distribution. So in MATLAB, I have a function to easily draw from the normal distribution. I get a number like minus 0.8. Now what I'm gonna do is I'm gonna compute the value of that point, the posterior right here, and compare this with the posterior value at my last point. This is for sure higher. I'm gonna accept the draw and I'm gonna reshift my proposal distribution to this value. So this is then the mean of the distribution, and I'm gonna draw a new candidate. Again, let's say here to the left, recompute the posterior. It is compared to your old posterior value. It's higher, accept. Always jump uphill. Then I have a new shifted proposal distribution. And let's assume that my next draw is in the tails right here. Okay, so it's 1. So I'm gonna compare my old posterior value to my new posterior value and see that this is now smaller. And now I'm basically computing another random variable between 0 and 1. And if this alpha is greater than this random variable, I accept the draw and I jump to this. So right here, black, I accept it. Okay, and I would reshift my proposal distribution, get a new draw right here. Now the blue curve right here is the histogram of my draws. I have now 5 draws, including the very first draw, and so far I have accepted all the draws. So I'm here, and now I get a new draw right here, new candidate. This is higher than my old value, accept. Okay. Next, I got one, whenever you see a red curve is, I have a new draw and I don't accept it because I'm not going uphill. I'm going to the tails, for instance, and then I draw this random number and then I'll decide not to accept this. Okay, and we continue to do this, jumping around. And if you have a look then at the histogram, you actually see that by doing this a large number of times, you see that we do stay very often close to the mode, but we do visit the other mode as well, every once in a while, because of this accept-reject algorithm. So let me stop at draw number 999. And you see that the histogram already is very close to the true posterior distribution. Now, this is the illustration of the Metropolis Hastings algorithm. So this algorithm returns many draws, and those are called a Markov chain, because each draw is dependent on the draw before that. And what we need for Monte Carlo integration is then take the mean or take some function on this draw to get the corresponding statistics. But there's a huge problem. The Monte Carlo integration only works, or the law of large number kicks in only for IID draws. And as you have seen, our draws are heavily correlated. One problem of the Metropolis Hastings algorithm, even though the theory will tell you that eventually you will start drawing from the true posterior distribution, you never really know when this really happens. So because of the initial autocorrelation in your draws. So what in practice we do is we draw 1 million draws and we get rid of half of them. Okay, to make sure to get rid of this burn-in autocorrelation. And then we only do our Monte Carlo integration on the last whatever percentage of draws I have left. Also, there are several diagnostics and tests that I can do to see whether the Markov chain has converged. So for instance, what you can do is if you have a remaining 100,000 draws, you can see whether the distribution of the first 10,000 draws is similar or the same to the distribution of the last 10,000 draws. So there are several other convergence and diagnostic tests, but I'm not going to go into these here. Now, you've seen that the proposal distribution is very important. And typical choices are normal distribution or student's t distribution. Now, theoretically, anything goes again. The theory of Metropolis Hastings tells you that eventually you will get there. However, in practice, it makes sense to have a good choice for this sigma of your covariance matrix of your proposal distribution to like re-weigh this. Typical choices are the identity matrix, the prior covariance matrix, or random numbers. Now, the best practice, however, is before you do the sampling algorithm, try to find the posterior mode by using numerical optimization. Try to find the highest value of the posterior, and that is the posterior mode. And then look at the covariance matrix computed via the inverse Hessian at that point. So this will give you a good choice for the sigma matrix for the covariance matrix of your proposal distribution. However, finding the mode might get really hard, and also the inverse Hessian is sometimes not well behaved. It's not positive definite. So then you have to like find other regions or shift it around, try different numerical optimization techniques, or fine tune this Hessian. Okay, so the point here is you do want to be in a region, you do want to start the whole thing in a region that has high posterior density, so you're not wasting too much time and going up the hill too much, but you're already visiting other areas of the proposal. Now, another choice that you should tune is scale this covariance matrix. And typically this is done by a scaling factor C that we multiply to the sigma matrix, and we try to scale this in such a way that we can make sure that we have visited the whole region of the parameter space. Okay, and what we look here is how many draws did we accept and how many did we not accept. So what is the average acceptance probability of the draws? So the key idea here being is that if you scale your covariance too high, if you multiply this with a very large number there, you will get a low acceptance probability. If you have a too low number there, you might get a too high acceptance probability. The problem is that in both cases, too low and too high acceptance probability, your draws are heavily autocorrelated. So you keep staying in the same area for too long. All right, that's basically it. What I want you to take away from Metropolis Hastings. It's a very neat little algorithm, very intuitive, very easy to program, and this enables us to estimate the parameters of a DSGE model. Thanks.